Welcome back, everyone. You sent us this latest paper from the harmonic team, and honestly, we've been pretty absorbed.
Yeah, it's definitely one worth talking about.
Right. Today, we're digging into Aristotle, IMO-level automated theorem proving. This one feels like it really shifts things in formal mathematics.
It's a big claim, tackling the IMO like this.
Exactly. And the goal isn't just, winning a contest. It's about getting machines to do formal reasoning, like really formal, verifiable reasoning at the top level. So for those just tuning in, here's your quick 60-second rundown. This AI, Aristotle, basically matched human gold medal performance on the 2025 International Mathematical Olympiad.
Which is already impressive.
Totally. It gave correct formal solutions for 5 out of the 6 problems, and that formal part is key. These aren't just essays about math, they're proofs checked by the Lean 4 system. Machine rigorous.
No hand-waving allowed.
None. How to do it? Well, it's this cool hybrid architecture. Think a super-scaled Monte Carlo graph search for the formal proof bit.
MCGS, yeah. Highly parallel.
Mixed with a more human-like informal reasoning part that sketches things out using lemmas. And there's also a dedicated geometry solver, Euclid, that's apparently crazy fast.
Based on alpha geometry, but way quicker.
The big takeaway. Combining these things, large models, smart search, and formal checks, seems to scale really well. It looks like a solid path forward for serious automated reasoning and math research.
Okay, but let's really underline why the formal verification part is such a big deal for researchers listening.
Yeah, go for it.
I mean, IMO problems are incredibly tough to begin with, right? We've seen systems like OpenAI's and DeepMind's get gold medals before. But those were natural language solutions. Humans had to read them and decide if they were right. Aristotle had to go way further.
Exponentially harder, you said.
Oh, absolutely.
Yeah.
The proof has to be written and verified in Lean 4. That's a formal language, a machine language.
Yeah.
It has absolutely zero tolerance for fuzzy thinking or logical jumps.
So the proof isn't just like convincing to a person, it has to be computationally undeniably true.
Precisely. And, that rigor, it actually gives a massive benefit back to the AI itself.
How so?
It provides this super reliable instant reward signal. If the lean checker says, okay, this proof works, the system knows immediately it succeeded.
Okay. No waiting for human feedback.
Exactly. And that speeds up the whole reinforcement learning cycle enormously, especially when you're trying to learn across lots of different math areas.
Okay, let's unpack this architecture then, because that hybrid approach, that mix, seems to be the real secret sauce here.
It really is.
Aristotle isn't just one giant model trying to do everything. It's more like a team of 3 specialists tackling different parts of the problem. Tell us about the main engine, the formal lean proof search.
Right, that's the powerhouse.
Okay.
It's running this highly parallel Monte Carlo graph search, MCGS.
Okay.
And the brain behind it is a very large transformer model. We're talking over 200 billion parameters.
Wow.
Yeah. And it does double duty. It acts as the policy deciding the next step, the next tactic in lean. And also the value function, judging how likely a particular proof path is to succeed.
And what does it look at when making those decisions?
It considers the current state of the proof in lean, obviously, but also the history, what steps it took to get there. And critically, if the other part of the system has generated an informal plan, it uses that too.
Okay, and just to be crystal clear on machine verified, this thing can't just leave gaps or assume things. Right?
No way!
It has to produce a proof that is totally complete in Lean 4. No gaps. You can't have anything like Sariax.
Exactly. For anyone not deep into lean, Sariax is basically like saying, trust me, this step is true, I'll prove it later. Or maybe never.
Right. A placeholder.
Aristotle isn't allowed those. Every single step, every lemma has to be proven from the ground up within the system.
Okay, rigorous. But that sounds incredibly difficult. How does it not just get completely lost searching through all the possible formal steps?
Well, that's where the second major piece comes in. The lemma-based informal reasoning system.
Okay, so why add informal reasoning if the lean engine is supposed to be the rigorous one? Isn't that just asking for mistakes?
It seemed counterintuitive, right? But it's a necessary trade-off. The formal search space is just unimaginably vast.
Too big to explore blindly.
Way too big. The informal system provides these, let's say, human-like intuition, the planning, the blueprint.
How does it do that?
It taps into all that existing informal math knowledge out there, like in textbooks and papers. It drafts an informal proof sketch first.
Okay.
Then it breaks that sketch down into smaller, manageable chunks, the lemmas.
Right, the building blocks.
Exactly. It then tries to formalize each of those lemmas into lean. And here's the clever part. It uses the feedback from the lean checker, did this lemma formalize correctly or not, to refine the overall plan and iterate.
So it's like sketching out a map before you start laying down the actual road network and checking each section as you go.
That's a great analogy. Designing the roadmap before pouring the concrete.
And then there's that third piece built for a specific, often tricky part of math contests, geometry.
Correct. They didn't just throw geometry problems at the main lean engine and hope for the best.
Probably wise. Formal geometry can be notoriously painful.
It really can. So instead, they built Euclid. It's a specialized engine written in C++.
Okay.
It uses techniques like deductive databases and algebraic reasoning. They call it DDRR. It's based on the ideas from alpha geometry, which was already strong. But Euclid is apparently optimized like crazy for speed. The paper claims it could be up to 500 times faster than the original alpha geometry.
500 times, that's significant.
It really highlights that sometimes you need these very specialized, super efficient tools for specific domains like geometry.
Okay, so you've got this informal system creating a high-level plan, guiding the formal search. Let's dive a bit deeper into that search itself, the MCGS. You mentioned it's not just a simple tree search.
No, it's more complex than standard Monte Carlo tree search,
No.
MTTS, which you might know from things like AlphaZero or expert iteration. The issue in theorem proving, especially in lean, is that applying one step, one tactic, might not just lead to one new goal. It can create multiple new subgoals that all need to be proven for that step to be valid.
Oh, okay. So it branches out, but you have to solve all the branches.
Exactly. That structure isn't a tree anymore. It's what they call a search hypergraph.
A hypergraph. Right, because multiple paths might need to converge, or one step leads to many required next steps. How does a system manage that? It sounds complicated to prioritize.
It is. It has to navigate this inherent and/or structure of proofs.
Okay, break that down.
So a proof state, like a main goal, is considered proven if any single action or tactic applied to it eventually leads to a full proof.
Yeah.
That's the OR part. You only need one successful path.
Got it. Any winning strategy works.
But a specific tactic and action only succeeds if all the subgoals it generates are eventually proven. That's the A&D part. You have to satisfy all the conditions created by that step.
Right, okay. So how does the search handle that and/or logic?
It basically treats finding a proof like playing a game, almost like Minimax. It wants to explore actions that look promising. High chance of success for the OR, but then for the resulting subgoals, the A&D, it tends to focus its effort on the one that looks hardest or least likely to be proven.
Tackling the bottleneck first.
Exactly. It's always trying to resolve the trickiest part of the A&D condition.
That sounds like a really smart way to manage the search explosion. And you mentioned the informal reasoning isn't just for the initial plan, it gets woven into the search process too.
Yes, absolutely. It's not just a one-off blueprint. The model actually generates informal output alongside the formal lean code during the search.
What kind of informal output?
Two kinds, mainly. There are informal comments, sort of like notes in the margin of the proof, and then there's a hidden chain of thought, the model's internal reasoning process, which has like a dynamic budget for how much thinking it can do there.
Huh. And does that actually help? Does thinking informally make the formal search better?
The training results seem to confirm it does.
Yeah.
Having that visibility into its own earlier thinking, even if that thinking isn't perfectly formal, genuinely improves the formal search performance.
It's like letting the system talk itself through the problem.
Pretty much, yeah.
So achieving this IMO gold level, it clearly needed a massive scale, that 200B parameter model, tons of parallel search. But you also mentioned a specific training technique that was crucial at deployment time. Test time training, TTT.
Ah, yes, TTT. This sounds really important for pushing performance on the hardest problems.
How did it work for Aristotle?
So the base model, even being huge, couldn't just crack every problem straight away. TTT is this iterative loop they run during the attempt to solve a hard problem.
Okay.
If Aristotle tries to solve a problem, or maybe a really tough lemma that came out of the informal plan, and it fails, it doesn't just give up. It takes the data from that failed search attempt, all the paths it explored where it got stuck, and it immediately uses that data to retrain the model right then and there.
Whoa, so it learns from its own specific failures on the spot.
Exactly. It specializes itself for the particular challenges of that problem it just failed on.
That sounds incredibly powerful, like targeted practice right when you need it.
Precisely. The paper says this specialization significantly boosted efficiency and, crucially, allowed the model to come up with complex lean constructions and abstractions ad hoc things it might not have known how to do before that specific TTT cycle.
So TTT was likely the key to unlocking those really difficult, maybe one or two hardest IMO problems that the base model couldn't get.
That seems to be the implication. That ability to self-correct and learn from immediate tough experience was vital.
Okay, the tech is fascinating. Massive scale, clever search, self-correction. But let's talk results. The proofs themselves. Did Aristotle just find the standard human solutions, or did it show sparks of, dare I say, creativity?
Well, that's maybe the most interesting part for mathematicians watching this space. The case studies from the IMO 2025 problems suggest it can think like a creative mathematician, sometimes even finding non-standard paths.
Okay, give us an example of that. Where did it differ?
All right, take problem 1, called sunny lines. The paper mentions typical human solutions often get bogged down in pretty complex formal geometry arguments.
Yeah, proving lines only hit certain edges of a shape, that kind of thing.
Right. Aristotle apparently sidestepped most of that geometric hassle.
Ow.
It found an algebraic proof instead, focusing on derangements. It was an elegant, fundamentally different approach that just required less tricky formal geometry.
That's cool. Finding a simpler, unexpected route. What about problem 3, Bonza functions? You mentioned defining new things.
Yes. This is a classic sign of mathematical insight, right? Introducing a new concept to simplify things.
Definitely.
The problem was about characterizing certain functions on natural numbers. Aristotle defined this novel auxiliary object, a specific set called Zillerallers, based on prime numbers where the function's value was greater than 1.
And this set-tel wasn't mentioned in the problem itself.
Nope, not at all. Aristotle identified it as useful, defined it, and then used it centrally in its final verified proof. That feels much more like proof synthesis than just searching through known steps.
Okay, and problem 4, sums of 3 divisors. This one sounds like it really shows the value of the formal verification part, not just for proving, but for fixing mistakes.
Oh, this is a perfect illustration of why lean is so valuable. So Aristotle generated an informal proof plan first, right?
Uh-huh, the blueprint.
Well, that initial blueprint actually had errors. Subtle language mistakes. It confused things like strictly decreasing versus weakly decreasing sequences, stuff humans might easily skim over.
Ah, I can see how that could happen.
But when the system tried to formalize that flawed blueprint in lean, the lean checker said, nope, this logic doesn't hold.
The verifier caught the bug.
Exactly. And the system didn't just fail. The formalization process effectively acted like a logical proofreader. It used the core ideas from the flawed plan, but repaired the logical gaps to produce a final lean proof that was sound.
So it turned a slightly broken idea into a working, verified proof. That's impressive.
It really shows the power of having that rigorous checker into grado.
And problem 5, the inequality game. Sounds like another example of technical depth.
Yes, definitely. Here again, it introduced a novel helper function, make-a-ho. It identified this as a useful invariant for the problem.
Another auxiliary definition.
Right. And technically, the proof showed real fluency with the MATLAB library in lean. Its first attempt used calculus, finding derivatives to get bounds.
Okay.
But later, it actually found a simpler way using a specialized algebraic tactic called linearith. And maybe most impressively, it used a relatively obscure tactic called filter upwards to prove a limit.
Filter upwards. Doesn't ring a bell from my undergrad math.
Exactly. It's usually found in more advanced analysis, dealing with filters and convergence, definitely not standard undergraduate material.
So Aristotle isn't just finding the easy paths, it's mastering and deploying pretty advanced tools from the lean library when needed.
That's the impression, yes. It shows deep competence within the formal system.
So Aristotle is clearly more than just an IMO contestant. It sounds like it's actually contributing to the broader mathematical ecosystem.
The contributions listed are pretty significant, yeah. During its training phase, just by proving things, it apparently filled several gaps in MATLAB, the main lean mathematical library.
Like what?
Things like Niven's theorem, the Gauss-Lucas theorem, connecting eigenvalues to characteristic polynomials, important results that hadn't been fully formalized yet.
Wow, okay, so it's adding to the formal knowledge base.
But maybe even more striking was the validation work. They pointed Aristotle at parts of Terence Tao's real analysis textbook, which he's been formalizing in lean.
Okay.
Aristotle found 4 exercises in the textbook that were actually false as written.
It found errors in Terry Tao's textbook.
And provided concrete counterexamples. For instance, errors in proposition 10.1.7 and exercise 9.1.15.
Okay, that is a massive statement for formal verification. If it can find subtle flaws in material written by one of the world's leading mathematicians.
It really underscores the value. Even the best human efforts can contain subtle logical gaps that only a machine checker might catch. And it did this while adapting to the textbook's specific definitions, which might differ from standard MATLAB.
That's adaptability too, and it wasn't just analysis, right? It handled other advanced stuff.
Yeah, the paper mentions it showed proficiency in areas like basic homological algebra and even Eisenstein series, so quite broad competence.
Now, before we wrap up, we should mention Aristotle wasn't alone in hitting that IMO gold standard in 2025 with formal proofs.
Right, important context. ByteDance's system, Seed Prover, also got there.
And it sounds like there are some similarities in approach, suggesting this might be the way forward.
Definitely looks like convergent evolution. Seed Prover also uses a hybrid strategy, a geometry subsystem combining informal and formal reasoning, breaking problems into lemmas.
So, similar building blocks. Any key differences in how they work?
The main difference seems to be in the core search or generation strategy. Seed Prover apparently leans more towards generating a whole proof attempt and then iteratively refining it.
Okay.
Whereas Aristotle, with its MCGS, seems to use the informal plan to guide a more step-by-step search through the formal proof space.
Interesting. Two different ways to orchestrate that formal-informal dance, but both reaching that gold standard.
Exactly. It reinforces that this blend of high-level planning and low-level formal rigor is really powerful.
And again, comparing this to the natural language NL solvers from, say, Google DeepMind or OpenAI.
Yeah, they also hit gold, performance-wise.
But their solutions needed human judges. Aristotle's achievement, like Seed Provers, is fundamentally about that verified rigor.
Precisely. It moves the goalposts from just can an AI reason, like a mathematician, towards can an AI produce verifiably correct mathematical truth.
And the answer seems to be increasingly yes.
So the big takeaway here is that the success of Aristotle really validates this multi-pronged approach. You take these huge language models, you combine them with smart guided search like MCGS, and you anchor everything in the absolute rigor of a formal system like Lean 4. That combination looks like a robust, repeatable path towards really sophisticated automated reasoning.
Yeah. And thinking about it, Aristotle's ability to not just solve problems, but to define new concepts, find errors in top-tier textbooks, generate these unique auxiliary definitions, that feels like more than just problem solving.
It skirts closer to actual mathematical creativity.
Right. It suggests that future versions might not just be tools for mathematicians, but genuine collaborators in research. The AI isn't just finding answers, it seems to be engaging with the creative and rigorous parts of doing math. That's a provocative thought to end on.
Absolutely. And if you, the listener, want to dig deeper, the formal Lean solutions for 5 of the 6 IMO problems are up on GitHub.
Oh, cool. People can actually inspect the code.
Yeah. And Harmonic also mentions you can register for early access to try out Aristotle via their website or the email listed in the report.
Excellent. We'll leave those links in the description for you. Well, hopefully this look at Aristotle gave you a clear picture of where automated theorem proving is heading. Quite an exciting development.
Definitely one to watch.
We'll catch you on the next deep dive.